introduces our seminar speaker today, I want to make a really quick announcement. So we have Professor Natalie Batalha here, and her run by the Shia Ismaili Muslim community of Canada. And she is going to be delivering a public lecture about exoplanets tomorrow evening at 7 p.m. at the Ismaili Center in Toronto. This is actually the second lecture in a series called Frontiers of Science and Innovation. Some of you may remember that we had David Spergel, the cosmologist, come and speak here and at the Ismaili Center last year. So just to give you some background and context for why this is happening, we are actually next door to the Ismaili Center in Toronto is, of course, the Aga Khan Museum, and these two together sort of serve as spaces, places of worship for our community, but also places for outreach to and engagement with the broader community. And Canada in particular has been chosen as the site for a lot of these Ismaili institutions, the museum in Toronto and the Global Center for Pluralism in Ottawa, because as a community we sort of feel that Canadian values are very much in line with our core values. Values of generosity, values of community service, values of tolerance and diversity, and a long-standing tradition of intellectual scholarship dating back 1,000 years. So that, including contributions to astronomy during the golden age of Islam. So that, in a nutshell, is the reason why the lecture is happening. And there's also one going to be taking place the following week, I believe, in Vancouver at the Ismaili Center there. So if you are interested in attending, all the information about the event is right here, including the registration link. But please drop me an email or come by my office to let me know if you're coming tomorrow evening so that I can give the organizers a sense of how many professional astronomers will be there. Thank you.
Right. So for those of you who work in exoplanets, you need no introduction. For those of you who don't have the fortune of working on an exoplanet, I'll give a short introduction. So she did an undergrad in Berkeley, PhD at Santa Cruz, postdoc at Rio de Janeiro, she was faculty at San Jose for a few years, moved to NASA and informed me that very recently she moved back to Santa Cruz. She's been instrumental in the development of the Kepler satellite. She won many awards, including the NASA Public Service Medal, and she's been included in Time's list of 100 most influential people. So today she's going to tell us all about the legacy of Kepler. So let me take it away.
Thanks for having me, everybody. It's a nice small group, so the talk can be very informal. We can have discussions, you can ask questions. I have way too many slides, but we'll see where it takes us. Kepler flew for 9 years, operated for 9 years, almost 10 actually. But recently it was in the news as running out of fuel. Just to remind you, Kepler's prime mission was to stare at one patch of sky unblinkingly for 4 years, and did so in the Cygnus region of the sky. That's where most of the statistical survey, the demographics of exoplanets comes from, is that 4-year survey. At which point we had problems with reaction wheels, and we had to be a little creative about how to keep the telescope running. One of the reaction wheels being broken, one axis of rotation was running open loop, and the engineers found a way to use solar radiation pressure and the fact that the spacecraft had an axis of symmetry right along its solar panels, which was fantastic. We leveraged that to keep that open loop axis of rotation under control. So. But that meant that we couldn't point at Cygnus anymore, and so we repurposed the mission as an ecliptic surveyor. And so every one of these footprints that you see along the ecliptic was one of our observing campaigns. And we ran like that we really doubled the lifetime of the mission. The mission was only baseline to run for 3.5 years, down from 4. Originally it was 4, but then NASA made us they cut our budget. And so we had to downscope, and the way we did that was we reduced the duration to 3.5 years. But through this engineering, we were able to run for another full 4 years of operations. But we always knew that we had a finite lifetime because the spacecraft requires hydrogen fuel on board to desaturate the angular momentum of the reaction wheels. They spin up with time, so every once in a while you have to fire a thruster to desaturate that momentum. And so the engineers, there's no gas tank aboard the spacecraft. We have to model how much fuel we actually use. What we do measure is the pressure in the tank, and so as the pressure decreases, you know that that's an indication that fuel is running out, and you can improve your models and try and predict how long it's going to last. And so our best predictions that it was going to end fuel sometime at the end of 2018. And sure enough, it started to show signs of low fuel, and at the end of October, there were lots of headlines like this: R.I.P. Kepler, so long and thanks for all the planets. The little spacecraft that could no longer can. It was pretty depressing. And all the reporters, they kept asking me, so how do you feel? Do you feel sad? I mean, on the one hand, Kepler was literally my whole entire career, except for my PhD, because that was done before the first planet was discovered. So it was an 18-year-long career, but I don't feel any sadness because we accomplished everything we set out to do and more. So I feel like no stone was left unturned, and I also feel like science is going to be done with this data archive for a decade to come. So there's still a lot to be learned from the Kepler data set. Interestingly, so we got this signal that the spacecraft was out of fuel. We downloaded all the data that we had available. We knew it was kaput, and we then had to actually power down everything. You don't leave a spacecraft on in space. You very methodically power it down to be good planetary stewards. You power it down and you stow it into a safe configuration. And so that was done a couple weeks ago on November 15th local time, which just so happened to be the anniversary of Johannes Kepler's actual death, which was crazy. That was not planned. Okay? And he's got this epitaph that he wrote: I used to measure the heavens, now I measure the shadows of Earth. So of course Kepler's has to be, I used to measure the shadows of Earths, plural. So it was a very special moment. Now, one small caveat, I put the 16th here because I had to be honest and put it in UT. So, okay, within a couple of hours, it was the anniversary of Johannes Kepler's actual passing, which was pretty crazy. The ball engineers, I captured this. This was, we took a screenshot of the operations log when it was done. So, it starts over here, and it's all just a bunch of gobbledygook. But, there are some poignant moments where they say that the Goodnight sequence has been initiated. And they had to do it a few times. Goodnight sequence command start. It took a few times. They issue the Goodnight sequence, and then they wait for a command back so that they know, or they wait to see that a command doesn't come back so that they know that it's actually off. And they had to repeat that process like 3 times to actually get it to turn off. But they did that, and then of course the last one is "So long, Kepler, thanks for all the fish." But they call this the Goodnight sequence, and it's actually a tip of the hat to the movie Interstellar and the Dylan Thomas poem. I don't know if you remember the movie, but in the beginning of the movie, when they're getting ready to go out and explore, there's this scene, and I went to all the trouble of pirating this off of YouTube for you, and now we don't even have audio, so it's my karma, right? But anyway, this is the clip, and they're in the operations room. They're talking to their commander, and maybe you can hear it.
It looks good for your trajectory. We've calculated 2 years to Saturn.
A lot of Dramamine. The gas from the family easily, sir.
We'll be waiting for you when you come back.
A little older, a little wiser.
not go gentle into that good night. Old age should burn and rave at close of day. Rage, rage against the dying of the light. Though wise men at their end know dark is right, because their words had fought no lightning, they do not go gentle into that good night. Rage, rage against the dying of the light.
So the ball engineers created the Goodnight sequence as a hat tip to this scene, which I thought was very appropriate. And so here's our raging into the night, right? This is what Kepler accomplished over those 8 years. Kepler, by the numbers, it traveled 94 million miles, observed 530,000 stars, confirmed 2,600 planets, with another 2,000 something that are still candidate planets. Almost 3,000 papers have been published and is still rising, actually. And all of that for just 3 gallons of fuel on board the spacecraft, non-counting launch, of course. It's a little kind of cheating, but also, 61 supernovae documented. Kepler did a lot of astrophysics too. In fact, I'll show just a couple of examples. It did solar system science. Here it is observing Neptune, and you can actually see Triton in tow, and there's another moon as well. Nereid is in there if you look carefully. But observing Titan in order to get these very high precision brightness variations, these are basically seismology of the surface of Neptune, which gives us information about the interior structure. So solar system exploration. The stellar astrophysics has been incredible, especially with regards to astroseismology. Tens of thousands of stars had frequencies detected, mostly evolved stars, but also some G-type stars, and extending down to a late-type G star, I think was the lowest mass star that had astroseismology. But it did amazing things, like, for example, being able to distinguish stars that are ascending the giant branch versus stars that are descending after helium burning. So you can actually pick out stars that are undergoing hydrogen shell fusion versus helium core fusion. And that has ignited the field, or at least put fodder for the field of galactic archaeology in order to map out structures in the galaxy. Also in the category of stellar astrophysics, gyrochronology is something that I was studying when I was a graduate student. The idea is that you can estimate the age of a star by looking at its rotation period, its spin period. Stars spin down as they age. They lose angular momentum through interactions between the stellar wind and their magnetic fields. And that acts as a torque arm for losing angular momentum. And so if you can do photometry, you can see indications of spots rotating in and out of view, and you can get the rotation or the spin period that way. That gets really hard as you're talking about older and older star populations, because not only do the time scales increase, but the amplitude of the variability due to the smaller spot filling factors also goes down. So it becomes very challenging. But Kepler observed something like more than 24 clusters ranging in age from like the upper SCO star forming region all the way up to like NGC 6811, which is a couple billions of years old, or maybe 1 billion years old. So it has a huge span of ages, but it also had such high precision that we could get the spin periods of much quieter, older, and lower massed stars. So this is an example. This is the Prasepe cluster, and the red points are from K2. K2 is the second generation of Kepler, the ecliptic surveyor. And you can see the huge numbers of points that have been added at the lowest masses. So here is a snapshot of spin of stars for a given age as a function of stellar mass. And so in order to map out rotation as a gyrochronology tool, you want to take these snapshots at many different ages. And so that's how you got the Skumonic spin-down law, for example. Back in the 70s, I think it was, or 80s, Skumonic gave this spin-down law, and that's how we use stars as a gyrochronometer. But what we're finding is that it breaks down as soon as you deviate from the G-type stars. As soon as you go to Ks and especially Ms, that Skumonic spin-down law is broken. Here's another snapshot. This is NGC 6811 data, so this is a significantly older cluster than Praesepe. The blue points are the observations, and the red points is actually a theoretical model of spin-down. And what the theoretical models all predict is that for these lower mass stars, you would expect the spin periods to be much longer. That is, you would expect a lot more spin down for that particular star at that age. So it's a huge deviation from the Skumonic spin down, and we're going to have to completely recalibrate the structure out here. I mean, look at this difference out here. So basically, the spin periods are plateauing in a weird way that we just don't understand. So that's a work in progress. And then, of course, Kepler is also quite famous for having observed not just the 60-some-odd supernovae, but because we stared unblinkingly, we were able to see the entire supernova event from start to finish, not just after it exploded. And what that allowed, what that enabled, was the observations of this tiny blip, which I think lasted 20 minutes, which is the moment when the core rebounding broke through the envelope. So it's the shock breakout.
Examples of that in the past?
I think that so they looked, there are other supernovae that were caught in this way that did not show a shock breakout. So this might be the only example of an unequivocal shock breakout. Yeah.
Is this the Goodnight paper?
I don't know. There's a reference, isn't there? I didn't put the reference, sorry. I might have forgot to change the font.
This claim is disputed.
I don't think that's I think it's, I want to say Smith is the first author.
There's one case where the claim for, so this is the claim for detecting the planar breakup, and I think it's disputed, and the issue there was binning in time. The analysis has been done by some.
Okay, I didn't think this one was controversial, but if it is, yeah, I would love to know. Okay, so those are just examples of astrophysics. I want to start, if I'm going to give a recap, I mean, what I'm going to try to do is just give a very brief recap of some of the science highlights. It's impossible for me to cover everything, and I'm completely ignoring fields like dynamics, like planetary dynamics, which you guys are just famous for and are doing such beautiful work on. So you have to get all of these people here to give talks about that. I'm also ignoring the body of work which is the mass radius, related to the mass radius relation. So all of the hard work to do the follow-up observations to get the Doppler masses and what the implications are for composition. So there are a lot of pieces I'm going to ignore, but I want to give some highlights and then to say a little bit about the final data archive and why it's so valuable, and then maybe look a little bit to the future. But let's start here. This was the very first light curve with Kepler that I saw. It was the very first data processing. There were only 3 of us in the room when it came off the pipeline, myself, John Jenkins, and Doug Caldwell. Doug is our instrument scientist. John is the guy who built the analysis pipeline. And we all looked at this light curve at the same time up here. So this is the transit of a planet called HAPI-7 that was discovered from the ground. Here is the ground-based observation of that transit event. And here is Kepler's data. And it was just like, wait, that's wrong. Where's the noise? Where's the scatter? I mean, it was like beads on a string. But what was really memorable about that moment is that all 3 of us, in unison at exactly the same time, said, "What's that?" What that is, when you zoom in, is this thing. It's an occultation. It's the dimming of light that occurs when the thermal day side of the planet goes behind the star. And what was special about it is that the depth of this is almost equivalent to the depth of an Earth-like transit around a sun-like star. So right out the gate, day one, first light curve, we just knew Kepler was going to be a success, all right? And this was that proof. And it was. I mean, we discovered over 4,000 planet candidates. This is the period radius diagram that I think is ingrained. It must be burned into your brain by now. You've seen it so many times. So we've got planet radius, orbital period. Those are the two things that Kepler measures. We've got blue and pink points. Those are planet discoveries done by other teams. Pink are transit discoveries. Blue are Doppler discoveries. You've got the puffed up distribution of the hot Jupiters here. Those are, their radii are inflated due to radiation from the parent star. You've got the Doppler detections over here, which have a lower dispersion. Before Kepler, 85% of the known planets were larger than Neptune. Now, after Kepler, 90% of them are smaller than Neptune. So the population is just completely different because we've lifted this blinder that was covering the small planets in the galaxy. Here is a plot of the habitable zone. We've got the temperature of the host star on the y-axis, and on the x-axis I have the energy being received by the planet, with the green, the conservative and optimistic habitable zone denoted in green. We found a few dozen of these that are smaller than 1.8 or so Earth radius. You can see the solar system planets here for comparison: Venus, Earth, and Mars. Venus and Mars mostly bracketing the habitable zone. This has changed because of the updated Gaia properties, which I'll talk about again in a minute. The new Gaia star properties, now we have a direct measurement of the stellar radius, which gives us a direct measurement of the planet radius, has caused some of these to move outside of the habitable zone. But and if you've seen that, you might be like, whoa, wait, Kepler didn't do as well as we thought. But what's not shown in those plots is that the same is true of the parent sample. Most of those stars also in this region also got bigger. So when you do statistics, those two things balance each other. So the answers actually don't change that much.
What are the units on the horizontal axis?
Earth units. Hey, wow, I'm like losing all my text. This would be 1 Earth insolation unit. Yeah. Okay, one of the key takeaways from Kepler is that the diversity of planets in the galaxy far exceeds the diversity of planets in our solar system. We found all kinds of crazy things, some of which were depicted in science fiction, but not all. Planets, these of course are all artist depictions, but there are planets in the Kepler data orbiting white dwarfs at least, or dead stars. We've got a whole class of ultra-short period planets that are the lava worlds. This is an artist rendering of Kepler 10b. This whole star-facing side of the planet is thought to be an ocean of molten rock, and that's not fantasy. We see evidence of that in the data itself through phase variations and an occultation, a secondary occultation. You take this more to an extreme and you actually get disintegrating planets. So these planets are photoevaporating in front of our eyes, and we see that through occultation or blocking of light from the tail of optically thick material that's emanating from it. It causes a very asymmetric transit-like event, right? So when the star first hits the limb, you get a sharp dimming, you get that ingress. But then as the tail comes online and then the planet leaves, it takes a long time for the level of brightness to come back up. So there's a whole class of these as well. We've got ocean, what we're calling ocean worlds. These are worlds we think are, by way of their bulk density, are actually covered in envelope of volatiles. Like Kepler 22b was the first of those. Circumbinary planets, planets orbiting stars in clusters. That has been really interesting for constraining migration timescales. You can look at the occurrence of very short period planets like the hot Jupiter population as a function of time for members of these different clusters. And it's like, now you see them, now you don't. You know, at very early ages, they're not there, and then all of a sudden they are. And that's because migration has taken place. So that helps us to put a constraint on that timescale for migration, when it's taking place and why. And then not really depicted here, but one of my favorites is actually the fact that we have found planets the age of the galaxy itself. And we know that through astroseismology measurements of the age of the stars. And that was a huge surprise as well. I don't think we really thought that there would be enough materials, you know, rocky material to form a rocky planet. And yet Kepler 444, the Kepler 444 system, has such planets.
Regarding the Occurrence, what migration time are you talking about?
I have to pull it up. It's still relatively quick. I want to, you know, within like 100 million years. I think one of the clusters that does show it is 100 million years old, and 100 million years. But also the statistics are very small. There aren't that many planets known to be orbiting stars in clusters. They're hard to find. Also exemplifying diversity is this plot. I think this is one of such a simple thing, but I think it's really one of the most amazing results of Kepler. It's just a radius histogram plotting the fraction observed, so just raw counts. But I colored the bars to roughly correspond to what we at least think of as rocky planets, as being brown, ice and gas giants, blue. And it just shows that the most common planet known to humanity right now is the gray area in between these kind of super Earth / sub-Neptunes that we don't know much about. Now, Kepler is a statistical mission, so we're going to take this observed distribution and just like when you do any census or poll in science, you do a survey and then you have to correct for the survey completeness and reliability in order to say anything meaningful about the intrinsic population. So this has been done over the years. It was done a year after Kepler started taking data. People started doing these calculations, and those early histograms looked something like this. So it's the same coloring, but I've excluded the Mars and Mercury sized bars because of small counts. But the other colors are the same. And basically what you see is the blue bars are suppressed and the brown bar is increased. And that's just the consequence of dividing or correcting for survey completeness and reliability.
What system paper? Because I haven't seen that yet.
This is my own calculation, actually. That's why there's no reference on it. And what I did was I grabbed all the planets less than 400-day orbital periods exclusively for G and K type stars. And I used the most up-to-date completeness and reliability calculations, but it's unpublished. Yeah. And these, our error bars are large, and actually we're going to see this become much more fine-tuned. So I saw these differences early on, but I didn't really pay attention to them. But they are going to turn out to be real. Yeah. The other thing I like to point out with this diagram is that if you take the average number of, now I'm plotting average number of planets per star, and I add these up, 0.4, 0.3, 0.35, you know, I get to a number greater than 1. And this is for a restricted part of parameter space, less than 400-day orbital periods, and only going down to 1 Earth radius, so you're not even considering planets like Mars and Mercury, right? But it implies that the, on average, because this is the average number of planets per star, on average, every sun-like star has at least one planet, which has implications for how we look at the sky, right? Of course, Wei Zhu told me today that the actual fraction of stars with planets is significantly smaller. It could be more like 0.3 when you average it out. But of course, again, you still have to consider that we're talking about a limited part of parameter space here. We haven't even begun to explore beyond the ice line yet. Okay, in 2015, we looked really critically at our survey, and we probed all the systematic errors. And that's what's being represented in this diagram. Basically, this is a posterior distribution for occurrence for one range of parameter space, namely between 1 and 2 Earth radius and periods of 50 to 200 days. So integrate over that, build it up as a posterior through sampling, and you get this orange histogram, and the mode is like it's something like 0.32, which is the average number of planets per star for that range. Okay? But then I start dialing knobs and say, well, what did I assume about the star properties? What did I assume about completeness, the survey completeness? What did I assume about the survey reliability? And as we dialed those knobs, we got posteriors that are actually significantly different. And that's when we realized we had to sit, gather our thoughts, and come up with a plan for how to get rid of all the tall tentpoles. How do we make more robust calculations of the survey completeness and reliability? We realized, for example, that the catalog, this is a posterior that's used from the original catalog of star properties compared to an updated catalog. And then we started wondering, well, what are we going to, we started realizing the importance of the star properties. And we knew Gaia was coming online in the future, but at that time we started making it a priority to observe the stars spectroscopically with our big telescopes in favor of doing high precision radial velocity even. Because we're looking at statistics, right? So it doesn't behoove us to do stamp collecting and just confirm individual planets. What we really wanted to do is get a homogeneous, uniform measure of what was going on statistically. Okay, so we also did things like transit injection and recovery. Every point you see in this radius versus orbital period diagram is a fake transit that was put into the pixel data, not the light curves, but the original pixel data. Those dimmings were inserted, and then we saw if our pipeline could recover them or not. And we paid special attention to these small 1 Earth radius planets at all orbital periods. And so when you do that, you can build up a detection efficiency curve. So this is kind of like a receiver operator curve or a cumulative distribution function. It's the fraction detected as you ramp up the SNR level. So an idealized, like the black curves, would be a Gaussian cumulative distribution function. So if you set a threshold and you say, I'm going to throw away everything 7 sigma and below, then you would expect at exactly 7 sigma to get it right half of the time, 50-50. So ideally, you would have at your detection threshold, which for us is about 7, you would have 50% detection probability. But when we go and we measure it, we find that, yes, sometimes that's true. For example, this star is very well behaved, this particular star, KIC 228585. But this star was not very well behaved. It had non-Gaussian noise. So it's going to deviate from a Gaussian distribution function, cumulative distribution function. And indeed it did. This is what we were measuring. So we have degraded completeness for this target at our detection threshold. We only got something like 10%.
So to what extent does this have to do with spottedness?
The question is, does it have to do with spottedness? It can. It can. Well, astroseismology is not going to hurt us very much because mostly these are 30-minute bins, so we're averaging over the time scales of astroseismology. But if you get to subgiants, for example, they start to show more variability. And the question is, what's the variability on transit timescales? You know, we have all kinds of filters that are taking out frequencies at different timescales, but we can't design a filter that takes out, something on a transit timescale.
My simple question is just, there's some subset of stars which may be undergoing a lot of magnetic activity when you happen to be looking at them.
Yes. So are there some stars that are especially active stars? Yeah. This was one of the reasons why Kepler was rejected in one of its incarnations. Ed Weiler at headquarters was skeptical that you could even see transits given stellar variability due to spots rotating in and out of view. And so the very first thing that I did at NASA when I got there as a postdoc, I had written an email to Bill Barucki, and I was doing Doppler reconstruction of spots on stars, and I was studying T-Tauri stars and young stars and activity, magnetic processes. And I wrote him an email and I said, I'm skeptical that you can do this because star spots are like bigger than planets and they rotate in and out of view. And he said, that's exactly why our last proposal was rejected. Can you come here and think about this problem? And that's how I ended up on the Kepler team. And so what I did was I did stellar population models, I invoked Skumonic law spin downs, and I calculated what fraction of our stars would be rotating fast enough that the timescales for variability would infringe upon the transit timescale. And so we knew already that we would be removing 30% of our sample just because of that. So certainly some of it is that.
So when it was working out the fraction of the stars that have planets, this is all now modeled accurately?
Yeah, so that's the point of this. Now we're going to empirically measure what our detection efficiency is. So we see that it depends on the color of the noise. We also see that it depends on stellar radius. So here's the same kind of cumulative distribution function, but now for stars of different sizes. And you can see that the completeness is degraded for the lowest mass stars, which could be due to convective processes. So ideally what we would like to do is we would like to put 100, 200,000 injected transits into the pixel data of every single star that we observed and run it through and check at all periods and epochs for planets and see what our detection efficiency is. If we had chosen to do that, we would still be calculating, I think, star number 10,000 right now. So that wasn't very practical. Yeah.
So how many times does your algorithm make a false detection point?
I'll get to that. That's reliability. Yes, that's important too. So because we computationally couldn't do that, we had to take a shortcut. And so what we did was we did that for a subset of stars, like 1,000 stars, of all different kinds of noise, like different noise properties, different radii, different surface gravity, just trying to sample a large variety of star properties so that we could parameterize the degradation and completeness as a function of all these parameters. And when we do that, we get a contour like this. So now what I've done is I've said, okay, for this star, kick 3561148, if I have a planet of this radius and this orbital period, how, that's going to have a certain signal to noise ratio. How frequently do I recover that signal in my injected data? And the contour tells you those numbers. And so this is the modeled detection contour, and this was actually measured. This is the same star, but doing the 200,000 transits aggressively. And so you can see that there's a lot more structure, but basically the shape of those contours is actually really well produced. So that's what we use for completeness. We have a really good handle on that, and all of these star-to-star models are published in the data archive. You can also get the original injection data if you have a special purpose need. So for example, if you're interested in how multiplicity of planets might degrade the completeness, we have data that you can use to explore that. If you're interested in the occurrence of planets around giant stars, you could go in and model that specifically. But what we've done here is provided a model for the kind of the bulk data. Okay, now what about reliability? How well do we recover planets, and do we ever recover false planets? There are all kinds of astrophysical signals in nature that mimic planets, and we've gotten really good at identifying the astrophysical mimics. We can even run stellar population models, take the fraction or the statistics on binarity, and we can create a mixture model to inform us. What we can't do is, what we couldn't do, we didn't have ground truth though for instrumental artifacts. And here is a period histogram of detections for Kepler in 2 different pipeline runs. This was an older pipeline run, this was the last pipeline run. They're different because we were always tuning knobs and trying to improve our detectability, our efficiency, and our reliability. But some things are common to both. For example, this peak here, that's the orbital period of the spacecraft, 372 days. All kinds of instrumental artifacts on that time scale that we have to worry about. And it creates an envelope of artifacts as well that aren't real, due to an electronic artifact called rolling bands. You also have very bright stars on the focal plane, like RR Lyrae, that creates ghosts other places on the focal plane. V38 Cygni also does that. And then you've got a time scale due to quarterly gaps. Once a quarter, we have to rotate the spacecraft to downlink data. That creates a gap, and that can also introduce artifacts. But again, the problem is, how do you model them? You don't have a ground truth. So you can't put in one of these artifacts modeled and see if you recognize it as an artifact on the back end. And this was creating discontinuities in our data. So here's kind of like the period radius diagram that you saw before, except now it's published as a heat map. And instead of radius, this is the basically equivalent to the signal-to-noise ratio of the detection. So large planets are up here, small planets are down here. And you've got this hot spot over here. And when you marginalize it, that's exactly that time scale of the orbital period of the spacecraft, right? So this was what happened when we blindly applied our previous statistical tests to the new data. And so we had to go back to the drawing board and create some new metrics that were really looking hard at like the shape of a transit, or looking at events on the focal plane in pixel space instead of looking at the events only in the flux time series, or looking, I already said shape, looking at individual transits to make sure that they all looked, we had sanity checks to make sure that they were all reasonable. And when we did those fine tunings, that peak almost went away. You can still see a tiny little hot spot there. So we still wanted a measure of what our reliability was. And the standard way to do this in statistics is like through bootstrapping. You take your data, you scramble it in some intelligent way, and you say, do I still see the signal that I'm interested in? So we could take the Kepler data and divide it into transit length chunks, scramble them, and then run it through a bunch of times and see how frequently you get something out at the same radius and orbital period. So that's standard bootstrapping, and that worked sometimes, but not always, because the exact way that you scramble, it's very sensitive to the source of your false alarm. That's going to dictate how exactly you scramble the data. So then somebody came up with another idea, and that was to take the data and flip it. So you zero mean it, unit variance zero mean, or just zero mean, and then you multiply by -1. And the idea is that the planet transits would become positive. So your matched filter technique for finding them isn't going to recover them. But the idea is that these rolling band artifacts were actually symmetric upon inversion and would be preserved. And so indeed, here's a histogram, another histogram of the number of detections in the normal data versus the inverted data, which here is inverted just for easy display, so you can see the symmetry. And here is that peak at the orbital period of the spacecraft. So this was the only way that we could think of to actually have some kind of ground truth going in. And so we pushed this inverted data through the pipeline and looked at how many signals came out the other end, the idea being that there shouldn't be any actual planets. And so through these two techniques, now we can measure both the completeness over this space of signal-to-noise ratio versus orbital period, and the reliability. And it's this bottom corner here that we're actually really interested in. This is the Eta Earth corner, where the small planets in the habitable zone are. You can see that we've tuned it for about 50% reliability and about 75% completeness, which is pretty good.
Wasn't there one astrophysical self-cleansing?
Microlensing signatures. Yeah, but they don't repeat.
Right.
Yeah. Flares can also do it.
This is a planet microlensing.
Yeah, microlensing is when you've got a background source.
Planet lensing is there's an event.
It's the microlensing companion stuff.
Right. Okay.
Yeah, but it's repeating, but the chances might only comes 3. The whole data set. So contamination.
Okay.
Are you talking about Doppler beaming? Is that what you're talking about? I missed that. Oh, got it. Okay. Yeah. The other thing that bothers us are flare events. They can line up with other instrumental artifacts. So we spent some time looking at the data carefully to It's one other measure. We still do the scrambling, and then now we've got the inverted data, and we're combining both of them to inform us about the reliability. Okay, I wanted to show this image about Gaia. So here is something like an HR diagram. You've got effective temperature on the x-axis, but here I'm plotting the stellar radius because these are the two quantities that are used in our measurements of the planet radius and the insolation flux of the amount of energy the planet is receiving at its orbit. So this is the kind of HR diagram of all of the Kepler stars that we did ourselves through pre-launch observations, through spectroscopic observations, calibrating against astroseismology, et cetera. But in order to create this, I mean, this is basically created from broadband photometry, plus some calibrators. So we had to use priors in order to get everything to fit on the main sequence. So basically, those priors are saying there's like 0 chance of a star actually being out here. So it forces things onto an actual HR diagram. But now we've got direct measures of the star properties through Gaia, and this is an actual physical HR diagram, which looks messier, but is actually extremely beautiful. You can see the helium clump up here. You can see metal poor stars. You can also plot on here a terminal age main sequence for different metallicities, and that's what these are. And using these terminal age main sequence lines, you can identify stars that fall way above them, which means that they're likely binaries. So this is the first time that we've had a way of identifying likely binaries that we can remove uniformly from the entire catalog in order to understand the population of planets orbiting single stars. So this is going to be very powerful. And so when you do occurrence rates, normally we've been measuring occurrence rates as a function of orbital period because the fractional uncertainty on the orbital period is so tiny, right? But it's not as much of a physical parameter. Well, it is one of the physical parameters, but what we'd really like to do when we're thinking about planet evolution, planet formation and evolution, we'd like to understand the effect of the disk on planet formation. We'd like to understand the effect of irradiation from the parent star, the effect of metallicity, all of these other physical parameters that are important for planet evolution and formation. But we couldn't really compute occurrence as a function of insolation flux because the error bars were so large. Insolation flux is r squared t to the 4th. So errors in stellar radius were making errors in insolation flux that were like 50 to 100%. But now with the new Gaia data, we're pushing down to errors in insolation more like 10%. And so that's going to enable the study of occurrence as a function of these physical properties.
So that actually measured all of the 500,000 stars?
Yeah.
Wow. They were all that bright, basically.
Yeah. Mm-hmm. Yeah, the question was, did Gaia measure the properties of all stars? And the answer is basically yes. Of course, there were some exceptions of junk, but yeah, for the most part. Just a short note about Eta Earth. These are all, so Eta Earth is the occurrence of small planets in temperate orbits, basically, something like the habitable zone. These are all published values of the occurrence for different kinds of stars, and you can see that they were spanning literally orders of magnitude in occurrence. This was very concerning because NASA wants to build a big telescope to direct image all of the nearest habitable planets, potentially habitable planets. And if you've got an order of magnitude in your planet yield estimates, that translates to a very different telescope that you want to build. But now with the Gaia properties, we can actually go in and improve this. And here are some measures of the occurrence. So the occurrence rate for M dwarfs has not changed. It still stands at about 0.24. This occurrence rate was from Heismolders this year for the G and K stars. That comes in at 0.36. And the answer, as I said, does not change very much when you put in the new Gaia data because, yes, the number of habitable zone planet candidates decreases, but so does the number of parent stars with sensitivity. So they come out to cancel each other. Let me say a little bit. Do I have until 10 after? Okay, let's go back to the period radius diagram, because there's a lot of information in this period radius diagram. There's a lot of structure. that's going to tell us something interesting about how planets form and evolve. The first I already mentioned once. I mean, there's a void of planets over here, very few planets. And there's a very characteristic slope here that is likely related to envelope inflation. So when a Jupiter-sized planet migrates close to its parent star, the irradiation does its thing. It heats up the upper layers of the atmosphere, but the surface gravity in that Jupiter planet is so high that the atmosphere is retained. But the atmosphere inflates, so you get a larger radius. Down here, there must be something similar going on. There's an inverted, mirrored slope here, but it's the opposite direction. The difference is that down here at small radii, you have much lower surface gravity. So my guess is that this slope is something related to escape processes. That is, if a planet down here tries to migrate in, it's going to be blasted by stellar radiation, quickly lose its envelope, and decrease in radius. That is my naive thinking. However, you also have to take into consideration the fact that So if that's true, what we're seeing down here in this slope is related to stripped core sizes. Yes?
Can you see the Fulton gap in this problem?
So I haven't gotten to that yet. That's this.
Okay.
Yeah. It's very confusing. Let me put that off for a second. Well, I can already say that there are two processes going on. One is orbital period or insolation flux. How much radiation is being received by the parent star? That's going to, in some cases, sculpt the outer envelope of volatiles if a planet indeed formed with them. So if a planet forms before the gas is dissipated, it can have, in almost all cases, some degree of a volatile envelope. But then it's going to be blasted by radiation, and given its surface gravity, that can wreak havoc. The other one is radius, so size. So this planet radius has got to be related to core mass, or surface gravity, if you want to think of it that way. But more likely like core mass, right? You have to start with a rocky core in the core accretion model, and then that enables the accretion of hydrogen, helium on the top and volatiles. So this might be some kind of diagnostic related to surface gravity. So these two effects are beating against each other. So this horizontal line over here that I've labeled gas accretion, the simple idea is that if a planet is tiny, it has a low surface gravity, and it's probably not going to accrete on a huge envelope of volatiles, whereas if it's above that line, you do get a lot of volatiles. And so this line is what you were referring to in the Fulton gap. Let me go ahead and show that. So if you can imagine a marginalization over orbital period between like here and here. So what we're going to do is show the distribution in radius given these occurrences, okay? So we're marginalizing over period. And that looks like this. So here's our histogram, average number of planets per star, and here's planet radius. And so remember, the ice and gas giants were very low. Then you get a sharp rise over here, peaking at around 2.2 Earth radius. But then instead of having that smoother shape, which we saw before, you've got an extreme gap in the middle, centered at about 1.8 Earth radius. And then it comes back up again. We saw hints of it in that other histogram. There was small hints of a gap. What's different between that histogram and this is that we have done significant follow-up observations with ground-based telescopes to firm up the spectroscopic properties of the host stars. So now we have very much fine-tuned the planet properties. And so what was blurred over before has now been made visible. All right? So where this gap is, I mean, when we looked at this, when we first saw this, our thought was, okay, volatile-rich planets on the right, rocky planets on the left. I'm not so sure that that's true anymore. We are seeing growing evidence through follow-up observations of planets to the left that have anomalously low densities, primarily through transit timing variations. Those are the observations that are giving us masses of low insulation flux planets, planets that are orbiting further out, that Doppler can't reach. Doppler measurements are all biased to short period planets that are highly irradiated. So the Doppler measurements are seeing all the stripped cores. But when you look at the transit timing variation measurements, especially like TRAPPIST, for example, although those planets have gotten heavier, Kepler 138 is another, and there's another paper that's going to be coming out soon that's going to show this in more detail. So the big question on my mind is, what is the physical mechanism driving this gap? And also, what is the compositional diversity to the left of the gap? And there's a lot more I could say about that, but I think in the interest of time, I'm going to wrap it up and just talk a little bit about the future. Kepler was an era of demographics. For the first planets were discovered, and that was like an era of stamp collecting, right? Every discovery was important and celebrated, every single one. Then Kepler released thousands of planets, and we entered this era of demographics, and we're still playing that out. But soon we're going to be entering the next era, which is going to be atmospheric characterization with telescopes like the James Webb Space Telescope. And we're already doing a little bit of that with Hubble. It's harder than this cartoon suggests, because the atmospheres of real planets are actually very thin. This is the transit of Venus, and you can barely see evidence of its atmosphere. You can only see it over here where Venus is projected against the blackness of space. The scale height of this atmosphere is like 5 kilometers. So you just don't have a lot of area through which the photons are passing. So it's going to be very difficult, and we have to find the nearest planetary systems in order to get the sensitivity to do this. Those characterization telescopes are going to be Webb, and then some of the next generation ground-based telescopes. I think I created this slide before I moved to Santa Cruz. You see Santa Cruz? I should put the TMT on here instead. I'll have to change that. But we do have these 30-meter telescopes coming online. I know for Santa Cruz, for Keck, the TMT, they've just accepted for design, or for the next phase, an instrument capable of doing atmospheric characterization. And it could end up to actually be a first-generation instrument if all goes well. Oh, I didn't update that either. I have updated it, but I must have pulled this from an older version. Yeah.
It's hard to see Jupiter, but maybe the fact that the most common planets are not the ones that are in our solar system is advantage, right? Because if you have a sun, then you can have an atmosphere that's comparable size to the sun core.
Yeah.
So then it would be easier to see the atmosphere.
That's a great point. Let me fast forward to this plot then, to take advantage of that and leave some time for questions. So what we'd like to do is prepare for a JWST legacy survey to really do a systematic study of the diversity of atmospheres. So what I did recently was I went into the database of all confirmed exoplanets, every single exoplanet we know of that's been confirmed at greater than 99% likelihood. And I got their insolation flux values and the temperature of their host star and their radius. So the size of the circle is the radius. And then I used the methodology of Eliza Kempton in a recent paper to compute it's like an SNR proxy for JWST. And I demanded that that SNR proxy exceed a certain threshold, which is telling me that the atmosphere is probably detectable with James Webb. And for the most part, that means that the host star is brighter than J equals 12. So I've culled the sample for all of the stars and planets that meet those criteria. I've also culled the sample for planets that have greater than 2 meter per second detectability, radial velocity amplitude. And here's why. If we want to understand the atmospheres of planets, if we want to understand even, let's say, the compositional diversity, and we're going to do this top-down approach where we're probing through the atmospheres, getting the properties of the atmospheres, and we want to know like the temperature pressure profile and abundances and all of those things that are related to this interior structure of the planet, we need to know the planet mass, because there is a degeneracy between the surface gravity of the planet and the mean molecular weight of the atmosphere. If you have a very light atmosphere, you can loft it. If the mean molecular weight is low, you loft the atmosphere. And if you have a low surface gravity, you loft the atmosphere. So to properly interpret Webb spectra, we must have the masses of the planets. And so here in my diagram of all the known planets that pass these SNR proxies, those that have measured masses, and these are all between 1 and 4 Earth radius. So we're looking at kind of the Earth to Neptune regime. Only those colored blue actually have masses. It's a very small number. And those that have a red circle around it are those that have TTV masses. And look at how much TRAPPIST-1 down here sticks out like a sore thumb, right? It's the only system of planets down there, and it's because they have those TTV masses. But basically, what we'd like to do is we would like to grid this up, and we would like to sample planets uniformly across both planet and star properties and subject those to JWST atmospheric characterization. But you see that we've got a ton of work that we have to do before that can happen, and Webb is going to launch in a couple of years, and it only has a finite lifetime. So if we really want to do a legacy survey and make use of this, we need to do some serious follow-up work, and that's what I'm at Santa Cruz to do. On the right is the planet yield predicted by TESS for the same exact criteria.
Just interrupt real quick. So,
Yeah.
So can you do this with high-res or can you
Yeah, both. Some of these are bright enough to do with APF at LIC, and others are.
Telescope time is not going to be true.
It's not. That's right. Yeah. Yes. So TESS will about double the sample because it's focusing on planetary systems or star systems that are nearby, with an emphasis for this low insolation flux part of the diagram orbiting the M-type stars. So that's something to look forward to as TESS proceeds. But we've got our eyes on this. We're looking at it carefully so that we can say goodbye to the last era of exoplanet exploration and look forward to the next. So I think I've extended my time. But thank you so much for your attention.
Maybe just one final question.
If we go back to the last plot, I'm just curious for the test systems. Pretty much all of those masters that you get, you come from DOC, right? RVs. There's such a short, like a 30-day period.
Yeah.
You're getting multiplied systems.
Yeah. Right. I mean, that's the downside of, I mean, these TTV masses are, you see how valuable they are. They're so, so valuable. But we're not going to get them with short duration, short baseline missions. This is an issue for Plato because Plato's on the designing board right now, and is, making decisions about what cadence and what baseline they're going to use. So there's time to influence that. And of course, TESS will get an extended mission, right? So it has these short windows, but it can repeat those observations after a hiatus. It comes back and does it again. And so through that way, we might build up some more of these TTV planets.